Good morning, good afternoon, good night. My name is Lluis Gifre, and I'm a researcher at CTTC in Spain. In this demonstration entitled Slice Grouping for Transfer Slices using Hierarchical Multi-Domain SDN Control of IP over WDM, we will showcase a joint effort between a number of partners of the TeraFlow European project and also the TeraFlowSDN open source group. Transport network slices provide connectivity services between endpoints over a shared underlying network and also enable to define, monitor, and enforce service level agreements. Besides, slice grouping enables to use clustering algorithms to group slices with similar constraints, for instance, capacity and availability, with the aim of optimizing the network resource utilization and improve the scalability. Also, hierarchical SDN controllers enable to delegate responsibility of managing specific network domains to specialized SDN controllers, which enables to accelerate the adoption of SDN on multi-layer and multi-technology domains. The TeraFlowSDN controller is a novel cloud-native and microservice-based SDN controller that is community-driven, it's open source, it's scalable, flexible, and extensible. It supports multiple technologies and it uses standardized protocols and interfaces to interact both on the northbound interface and on the southbound. In particular, some of the use cases that are addressed include IP over WDM, interdomain connectivity services, security, and so on. On the northbound interface, it implements, for instance, IETF Layer 2 VPN and IETF slice models. And then on the southbound interface, it implements netconf openconfig, P4, ONF transport API, IETF topology, and a number of other protocols and interfaces. In this demonstration, we will showcase, as said, the new capabilities of the TeraFlowSDN controller to optimize the network resource utilization using slice grouping techniques and also to control multi-technology domains through hierarchical controllers. In particular, we will consider IP, microwave, and optical domains. To explain briefly what slice grouping means and how it works, here we can see an example of a slice template. In particular, this is a slice template named as gold that defines the specific metrics, in particular the one-way bandwidth to be 50 gigabit per second and the availability 70%. Then we can define a number of clusters based on these metrics. For instance, we can see here in this table the four classes or clusters in this case that we are using for this demonstration, which are the bronze, silver, gold, and platinum with different values of availability and capacity. We executed a simulation creating a number of random slices with random values and mapped them using this clustering algorithm to see how is the distribution of slices in this simulation with these parameters. So we see that the bottom left part corresponds to the bronze, then this part are the slices that are mapped to the silver, these ones are the slices mapped to the gold class, and the upper right are the platinum. We can see in red with these red dots the centers of the different clusters that we used. The workflow for slice grouping is this one. Whenever an OSS, VSS, or a user demands the creation of a new slice with SLAs by means of the MBI, the MBI delegates this creation to the slice component, and the slice component then runs a slice grouping algorithm that essentially initializes a k-means algorithm with the set of configured slice groups. These are the centers of the clusters, and then it maps the SLA values of availability and capacity in this case to the clusters and tries to identify which is the group that better fits with existing groups. In case the group already exists, what it does is just to map the new slice to the existing one and returns a control to the OSS BSS. Or if new services needs to be created, then it triggers the creation of the services to the service component. And also, this service component delegates the configuration of the devices to the SBI component. We will see later the architecture of the TeraFlow SDN controller that we used in this demonstration. Infinera XR point-to-multipoint coherent optical technology is a novel technology that enables to reduce the number of transceivers that are required to interconnect a number of customers in the access segment to a specific transport network. In this case, the traditional point-to-point optical solutions imply the creation of point-to-point connections, which require to use n+1 multiplied by 2 transceivers, where n is the number of endpoints to be connected. The novel XR technology enables to reduce the number of transceivers by using point-to-multipoint connections and then replacing the intermediate aggregation block by just a simple optical combiner and then terminating the optical connections directly on the hub. Then, to integrate the XR constellation and the optical domain, what we did is to implement a small setup where the hub transceiver is connected to a passive optical splitter coupler, splitter decoupler, and then the different leaves of the splitter are connected to some endpoints of the optical domain. In this case, it's managed, the optical domain, by an open line system controller, and the transceivers are managed by an Infinera pluggable manager controller, IPM for short. Sorry, I forgot to say that then on the other side, the optical domain is connected to the leaf transceivers. And then both the IPM and the OLS controllers are managed by means of the TeraFlowSDN controller, and we use a proprietary REST API for the IPM, and then we use standardized transport API for the OLS. This is the architecture of the complete setup. In particular, we can see here that we have a parent TeraFlowSDN controller that is in charge of managing the end-to-end connectivity. And then we have a number of child SDN controllers. The parent SDN controller, well, we have here just a subset of the relevant components that we are using, in particular the MBI. We are using the SBI to interconnect with the different intermediate controllers. Then it's relevant also the context, because it has a database with the information of the different resources in the network. The service component is in charge of configuring the services through the SBI, and Slice is in charge of configuring of creating the services through the service component. Then the path computation is also used to compute the paths for the service component. Then we have another instance of TeraFlow, a child TeraFlow instance, that interacts by means of the IETF layer 2 VPN data model with the parent TeraFlow controller. The child controller, in this case, is in charge of controlling the IP domain, and in particular, it uses OpenConfig to configure the ADVAR routers at one end and the other end of the network. Then we have also the microwave SDN controller that is in charge of controlling the microwave link between a couple of routers. Then we have an OLS controller that is in charge of controlling the optical mesh. In this case, it uses Transport API for controlling the optical network. And we have also the IPM controller that is in charge of controlling the XR transceivers that are on at both sides of the optical mesh. Let's start with the demonstration now. The demonstration is split into parts. The first part is about the hierarchy. The second part is about the slice grouping. So for the hierarchy, we have here a number of controllers. So this is the interface for the OLS controller at CTTC. This OLS controller is managing a 4-node network with this connectivity. And right now, if we check connectivity services, there is no service created. The microwave controller is in charge of controlling the radio link. Right now, it has a couple of devices that are connected by means of the radio link. And if we check here, even when there are some connectivity services already established, what we will do is with the creation service, we will create another one, the 111. Then for the XR, we see here the Constellation. We have on, not XR, the IPM controller. We have on one side the hub transceiver, and on the other side, the 2 leaf transceivers. So here, if we check, right now there is no connection established. Now we check here the child TeraFlowSDN controller. It has, in this case, 3 routers that are interconnected, forming a mesh. We can see here that we have all the devices enabled and onboarded. And right now, there is no service or slice created here. And this is the parent TeraFlow. We can see here that it has a number of devices onboarded. It has the 2 data centers we want to interconnect. Then we have here the child TeraFlow controller that is in charge of managing the 3 routers that are interconnected. Then we have here the microwave link, the microwave controller that is in charge of controlling a microwave link here in between these 2 links. The IPM controller that is in charge of controlling the XR transceivers. At this side, we have the hub, and here we have the 2 leaves. And then we have here the OLS controller in charge of the optical mesh. And this is the optical splitter that interconnects the hub with the number of endpoints in the optical mesh. Right now, we have no services and no slices created. So now let's start by creating the service. And for that, what we will do is to use a descriptor defining that we want to create a connectivity between the 2 data centers. And then we just provide here some configurations that are required. I mean, some basic configurations defining which is the mapping between the data center subnetworks and the transport network. So let's start with the demonstration. For that, we will onboard this file, the one that I was showcasing. We press submit here. It will take a few seconds to do the processing. Okay, so it's done. Now, if we check here, the list of services, we can see that 5 services were created and they have dependencies among them. For instance, the data center to data center, in this case, is connecting the different, the 2 data centers between them. And this connection is supported by a subservice, in this case, the 8.2.1, that is connecting 8.2. It's again a layer 2 service. It's connecting the routers in the IP segment. Okay, here we can see it's 149. It's connected with 199, and we see that the connectivity between the two routers is again supported by a couple of subservices, 94 and DF. Okay, if we check, 94 is the one. It's again layer 2. It's the one for the microwave link. We can check it quickly. It's this is the service for the microwave, and then the DF is the one connecting the hub to the leaf. Okay, so here we can check. This is the connectivity between the hub and the leaf. And again, we can see here that the 82A service is created to support this connectivity. If we go back and check, the 82A in this case is the connectivity between the ingress and the egress endpoints of the OLS. Again, we can check here briefly the service. Okay, so now what we will do is to check that in the different intermediate controllers, the connectivity was established. So here we check. In the slice, we can see that the slice was created. It's the 82OA. If we check here, it's this one, 82OA. Okay, it's for the connectivity between the routers. That means it was delegated to the child controller. And we can check here that this connectivity is supported by subservices, in this case, the same identifier. Let's go now to the services. We can see that the service was created, is active. We can check here. We can see the configuration that was defined for this subservice, and we can see which is the connectivity. Remember that between 149 and 199, we have the complete setup. Okay, and that concludes the first. And now we can see here that it was created for the IPM, the connectivity service for the XR pluggables. We can see also that the connection with VLAN 111 was created on the microwave controller. And also, if we check here at the OLS, we can see that the optical connection between the source and the destination SIPs, Transport API Service Interconnection Points, was created. And now that concludes this part of the demonstration. I will jump to the second part. For that, I have another instance of TeraFlow that I configured with a small transport network with some routers. In this case, we have seven routers. They are emulated for the sake of accelerating the demonstration. And right now we have no services and no slices created. We created a Grafana dashboard to show how is the progress of creating the slices. In this case, we will create just 10 slices to showcase the grouping. So for that, what we will use is a load generator. Here I will put 10. I will create layer 2 slices, and then I will start the generation. Now, if we go here to the slice, we will see in a few seconds that the different slices are being created. We can see here, for instance, the bronze. We can see here silver. We can see gold, and we can see here a platinum. So that will be created, and also they will be torn down in few seconds. Okay. Well, we can see if we check here in the service tab that the different services are being created and removed progressively. Okay, there is one remaining. So now if we check, the services are removed here. Okay, and that concludes the second part of the demonstration. So in this demonstration, we showcase it to the OFC audience a slice grouping mechanism to provide end-to-end SDN orchestration through multiple technology-based SDN domains using the new release of TeraFlowSDN Cloud Native Controller. Also, we showcase it the capacity of managing in a hierarchical manner a number of domains. And well, if you like the TeraFlowSDN experience, you can join us. I mean, the participation is open to ETSI members, non-members, individual contributors, and users. And if you want to learn more, you can join, and you can find us at tfs.etsy.org. This work received funding from the European community through the TeraFlow project, and also from the Spanish ministry through the Relámpago and the 6G microSDN cloud projects. Thank you very much for your attention.